To reach orbit, a launch vehicle must accelerate to 9.4 kilometers per second. It has to achieve this velocity while carrying its own guidance systems, payload, and the sheer mass of its fuel and tank structure. Analytically, this diagram shows a brutal mass fraction feedback loop. Every kilogram devoted to the structural integrity of the rocket reduces the efficiency of the payload it can carry. If you add mass to strengthen the hull, you have to add exponentially more fuel to lift that new mass. That additional fuel increases the overall weight again, driving the costs even higher. Space access was physically possible, but the physics of escape velocity created a self-reinforcing economic trap. Early aerospace engineers working on rockets like the Saturn V were forced into a corner by these unyielding physical laws. Acceptable design was predicated on total disposability. A rocket was built with the same underlying assumption as a matchstick. It was a machine optimized to perform its function once before being discarded. For decades, orbital launch was a financial loss mechanism. The high cost of access was an unavoidable consequence of the physics required to leave the planet. The sheer scale of the hardware being thrown away in the pursuit of orbit was staggering. The booster stage, the most expensive part of the system, was treated as a disposable container for a single flight. Returning that stage required surviving 3 simultaneous physical threats: extreme thermal loads, severe aerodynamic instability, and precision landing control without structural failure. When a massive, unguided cylinder attempts to fall back through the atmosphere at hypersonic speeds, the result is predictable destruction. Early rockets were not thrown away due to a lack of engineering imagination. They were discarded because no control architecture existed that could survive a hypersonic fall. Early reentry physics research provided the first crack in this assumption. Engineers realized a controlled atmospheric descent is predictable if attitude and drag can be actively managed. Initially, this insight was restricted to small-scale applications. It was effective for low-mass human return vehicles like the Apollo capsule, where heat shields and ballistic trajectories could be carefully managed. The problem was one of scaling. No control architecture existed to stabilize a 100-foot falling fuel tank, meaning the booster remained disposable. As private launch systems began iterating faster than state programs, they reframed the problem. Instead of trying to prevent destruction, they focused on how to preserve enough structural integrity through a controlled failure. This change in definition, surviving within repairable limits, provided a viable path to orbital recovery. Success no longer required a perfect landing, only a salvatable one. The solution emerged in layers, starting with thrust vector control. Engineers improved precision until engines acted as active stabilizers, steering the booster against atmospheric pressure. Standard wings would fail at these high speeds. Instead, engineers introduced grid fins, small aerodynamic surfaces that reclaim atmospheric control authority as the booster falls. Even with steering control, the vehicle faces a lingering velocity problem. It is still falling too fast and carries lethal momentum. This forced the introduction of propulsive landing burns. The rocket reignites its engines mid-descent, using the fuel system that lifted it to orbit to undo its fall. Every second of this burn is a negotiation, trading remaining fuel for structural survival. These combined mechanisms repurposed the falling booster. It was no longer a passive ballistic projectile, but a highly controllable object. But mechanical control alone was not enough. Pre-programmed flight paths fail during the chaotic realities of atmospheric reentry. Where earlier spaceflight relied on rooms of engineers to calculate trajectories, modern guidance systems moved onto the vehicle itself. Onboard computers process wind shear and vehicle orientation changes milliseconds at a time. The onboard computer constantly recalculates the burn rate against real-time atmospheric feedback to stave off instability. The rocket is no longer just following a ballistic curve. It is an active system continuously correcting its own collapse. The first successful landings revealed a second constraint. A recovered booster that takes months to inspect and rebuild is industrially useless. Economic viability required a new optimization layer. Hardware had to be designed for rapid turnaround rather than just survival. This required physical changes. Materials were reevaluated for thermal fatigue resistance, and engine components were modularized so they could be swapped out quickly. Structural inspection became digitized. High-resolution scanning was implemented to instantly assess the airframe post-flight, replacing manual inspections with high-speed data. The industrial impact of these changes was significant. It integrated spaceflight into a semi-industrialized system of rapid logistics and recovery speed. The architecture of space access shifted. Launch vehicles moved from handcrafted machines toward systems resembling commercial aviation maintenance cycles. As turnaround speed increased, the cost per launch began to decouple from raw material costs. The economic model moved to a loop of build, recover, iterate. Yet this system is not stable in an absolute sense. Reusability does not eliminate physical risk, it only redistributes it across multiple cycles. Humanity did not solve rocket physics. We solved economic survivability within those laws. The booster that returns is not a conquered machine. It is a system operating continuously at the boundary between controlled failure and functional survival.